Well, I guess we should start. Let me introduce to you myself first. I'm not a native English speaker, which you probably will hear by my accent. I'm from Germany, and to tell you a little bit about myself, I've been doing a lot of system administration for a lot of years, and started about 5 years ago providing security training and consulting, mostly in the open source area, and have been doing a lot of, well, penetration testing during that time at different places, at different customers. And today I would like to tell you a little bit about my experiences using and testing an open source IKE daemon implementation, and the tool I developed during that while testing. So if we talk about IKE, we have to talk about IPsec. If we talk about IPsec, we're speaking VPNs. And I don't know who of you have heard the keynote by Paul Simmons yesterday morning. Paul, well, somehow required secure protocols for what he was proposing, his deparameterization of the networks. And IPsec mostly is thought to be a secure protocol. IKE is thought to be a secure protocol, and it probably is, but the way it is designed. But there are a lot of problems within the different implementations out there. There are several IKE implementations, IPsec implementations, and not everybody is actually following the standard to the dot. So we should take a closer look at those different IKE implementations to see whether they are implemented correctly or whether they have their flaws. Most VPNs today are based on IPsec, and if you look at IPsec, there are essentially two protocols. The authentication header protocol and the encapsulated security payload protocol, which do the work, which take care of guaranteeing integrity, confidentiality, but these protocols actually do not exchange keys. So when you actually want to set up a VPN, you need some keys to encrypt and to authenticate the packets with, and you need somebody who takes care of that. And there are two protocols actually available and used today. One of them is the Internet Key Exchange Protocol. The Internet Key Exchange Protocol is the protocol used most often. There's another protocol not known to many people. It's called Futuris. It's, for example, used by the OpenBSD people. They've got a Futuris daemon which can be used to exchange keys. If we take a closer look at the Internet Key Exchange Protocol, it's very complicated. There are a lot of standards that actually define how the Internet Key Exchange Protocol should work. So it is based on several other protocols, several other frameworks. I've just listed a few of them here. There is the ISA-KMP protocol, which is defined in the RFC 2408, which provides a framework for authentication and key exchange. There's the Oakley protocol, or the Oakley framework, defined in its own RFC, which describes a series of key exchanges, which are called modes. There's SKey, and then there's IKE itself, and IKE essentially is a protocol which is using parts of all these other protocols I just mentioned. So implementing IKE or IKE is not very simple and is probably error-prone. Although IKE itself is probably a good design and quite secure. So if you take a look at IKE more closely, it actually does its work in two phases. There's a phase one, which has again at least two different modes, which are called the aggressive mode and the main mode. There's another mode, it's called base mode, which is not used that much today. The aggressive mode uses 3 different messages to do its work. The main mode uses 6 messages and offers identity protection doing it. And once phase 1 is done, once phase 1 was successful, there's a phase 2, and phase 2 fortunately only has one mode, which is called the quick mode, but relies solely on the security of phase 1. So in phase 2, we don't have any additional security negotiated. We just rely on the security negotiated in phase 1. If we take a look at the aggressive mode, there are several ways we can use to authenticate during phase 1. We can use pre-shared keys, which essentially are passwords. We can use RSA signatures. We can use RSA encryption. And there even are 2 ways to encrypt in phase 1 using RSA keys for the authentication phase. So if we take a look at the aggressive mode using signatures, those are the messages that are exchanged. So we've got the initiator, which sends a packet to the responder. The responder is usually the VPN gateway accepting the connection. And the packet that is sent consists of a header, of a security association payload, a key exchange payload, a nonce payload, an identification payload, which are all packed into one packet. The responder answers using a header, his own security association response, his own key exchange payload, his own nonce payload, his own identification payload, maybe an additional certificate payload which contains his own certificate, and to authenticate, lastly, it adds a signature payload. And then the initiator sends again his own certificate and the signature payload to authenticate. If the responder has any kind of flaw within the code that passes the key exchange or the security association or the identification payload of the initiator, we might have a problem, because we can send this information without authenticating ourselves before. Let's take a look at the main mode, which is a little bit more complicated. It has got 6 messages. And again, we see pretty much the same payloads. The only difference between the main mode and the aggressive mode pretty much is that the last 2 messages, in the last 2 messages, the header has got this little star over here. And what the star means is that everything behind the header is encrypted. So we've got some kind of further security within the main mode, further security which encrypts the identification payload, the certificate, and the signature payload, so that an eavesdropper that listens into this connection cannot see the identification payload or the certificate in clear. Therefore, the main mode is often called the identity protection mode 2, because the identity is transferred encrypted. The aggressive mode doesn't support this. The headers don't have the star, which means that every payload transferred is not encrypted. So the identification payload and the certificate payload is transferred without any encryption. There are several different payloads which are supported by IKE. There are the security association payload, the proposal payload, the transform payload, key exchange payload, identification payload, certificate request payload, the hash payload, signature, nonce, notification, delete, and vendor ID. The sheer number of these payloads makes it very difficult to implement an IKE implementation that actually handles all these different payloads correctly. To further complicate the whole situation, most payloads are built up like this. This is a generic payload structure, we've got 16, we've got 4 bytes which are constant, the next payload byte, 1 reserved byte, and 2 bytes which define the length of the payload, and then we've got a variable length payload. So any kind of these payloads might have a buffer overflow in the IKE implementation. So if the IKE implementation does not check the length or buffers, there might be a buffer overflow. And in fact, there have been buffer overflows in IKE in the past. If we take a further look at IKE and the IKE importance today, IKE exchanges the keys in almost all IPsec-based VPNs today. I'm not aware of any vendor at the moment, any commercial vendor at the moment, that does not use IKE to exchange keys for an IPsec-based VPN. If anybody of you does know such a vendor, I would be very interested. If we can compromise the IKE exchange, if we are able to introduce buffer overflows or stuff like that, or if we're able to somehow use certificates which are not valid, if we are able to use signatures which are not valid, we can compromise the IKE exchange and can attack the Achilles heel of the VPN. So once we can do that, we usually are done with the attack, because if you take a look at your VPNs today, probably most VPNs are used to enable, well, are used to give you full access to your internal network. Once you've authenticated to your VPN, you're in. Because usually your boss wants full access to his database while he works from home. So most VPNs actually give you full access. So let's take a look at IKE problems after we've looked at the complexity. There's at least one design flaw that is known and that has been known for some time, and that's, that can be used to attack IKE when you're using IKE with aggressive mode and pre-shared keys. If we go back to the aggressive mode exchange, you see that there are 3 packets passed back and forth, and that the identification is passed and clear. And this is the aggressive mode exchange using signatures, but if you use pre-shared keys, it's pretty much the same. What actually is exchanged then is a hash here, which is encrypted using the pre-shared key, or based on the pre-shared key. And what you can do, and what was first published by Anton Rager, is you can do a brute force or dictionary attack on the used pre-shared key. So if the pre-shared key that has been used to implement the VPN can be guessed using a dictionary attack, it's quite easy to attack the authentication phase. First published by Anton Rager, and the first tool that implemented that was called iCrack. If you're interested in iCrack, you can find iCrack on SourceForge. It's icrack.sf.net, and you can download it there, and it's a nice tool which is able to crack your pre-shared key aggressive mode VPNs offline. So you just sniff the exchange from the wire and crack it offline, or using machines which are capable of doing it. Further IKE vulnerabilities. Those are now vulnerabilities that are not inside the IKE protocol itself and the IKE design, but in different IKE implementations. And I've just used a few of those. I've just listed a few of those that are listed in the Security Focus vulnerability database. So there are several bits here now which you can look up. It's a Security Focus vulnerability database, and there are several vulnerabilities in the XAuth implementation, which is an additional IKE implementation which allows you to use usernames and passwords. There's a denial of service vulnerability in the ICK-MPD of OpenBSD. There are different vulnerabilities in several clients, which can be exploited using excessive payloads, and there are different vulnerabilities within multiple vendor IKE implementations which are not correctly authenticating or verifying certificates which are used in the authentication process. The security vulnerability database lists altogether about 32 different IKE vulnerabilities. Well, listed them at the time I looked them up, which is about a couple of weeks ago. Even simple bugs are not found if nobody looks for them, which can be quite easily demonstrated if you take a look at two simple bugs in Raccoon, one of which was detected by myself, the first one. The second one, well, was detected by myself too, but unfortunately Thomas Walpurski found it too and already published it a couple of weeks ago. So I couldn't present it here. Anyway, what actually happens, and that's what I want to show you later on, is that the Raccoon IKE daemon can be contacted using IKE, and what usually should happen if you use X509 certificates for the authentication is, I go back to the main mode, we send each other security association payloads and propose what kind of encryption we want to use, what kind of hash we want to use, what kind of Diffie-Hellman group we want to use, and they negotiate those. Then we send key exchange information for the Diffie-Hellman exchange and nonces, and last but not least, we send our own identification, our own certificate, and usually a signature which authenticates ourselves to the peer. The signature should be generated using our own private key. So if you're familiar with private and public keys, we send the public key within the certificate and we sign, and we create a signature with our private key, and the responder which gets this information can check our signature using our certificate. Well, if you send Raccoon, this older version, it's fixed now, if you send Raccoon any kind of valid certificate and don't create a signature at all, it says, hey, okay, I'm fine, we're done with it. The certificate was fine and I don't even check the signature. That's the first one. That was fixed quite fast. It took the people developing Raccoon a couple of days to fix that. And then the second one was found. And what the second one actually does is, if you now again contact Raccoon and send Raccoon your certificate and generate a valid signature, Raccoon does not check the certificate anymore. So if you've got a certificate which is not valid anymore because somehow the validity date is in the past, or if you've got a certificate that has been revoked, Raccoon says, hey, fine, I don't care if the certificate is revoked, I allow you anyways into my VPN. So those are quite simple vulnerabilities which were present in Raccoon for at least a couple of years, and nobody found them. Why not? Because probably everybody always used valid certificates and valid keys, and nobody wondered if he could authenticate to Raccoon 2 using non-valid private keys or using non-valid certificates. So what I thought back then was that we need a tool to test such IKE implementations. We need a tool to somehow find out if the IKE implementation actually does what it is supposed to do, if it actually implements the IKE standards as they are defined. Since there are numerous IKE implementations out there, and a lot of them are closed binary IKE implementations, we cannot just take a look at the source code. which is quite easy. And when you take a look at Raccoon or the IKE-MPD or the FreeSwan tools on Linux and stuff like that, you can take a look at the source code. But a lot of implementations are closed source, so we need a tool to test those, since they might have numerous buffer overflows or strange or wrong certificate handling or just other straightforward bugs. To give you an idea what kind of buffer overflow problem IKE implementations might have, there was one in Checkpoint, which was found, I think this year too, either the beginning of this year or last year. Checkpoint had improper handling of certificate request payloads. Since, go back to my main mode, since we're exchanging certificates here, if you take a look at the messages again, this cert underscore I and the cert underscore R are in brackets. And what these brackets mean essentially is that those are optional. So you can send your certificate, but you don't have to send your certificate. If you don't send your certificate, the responder must have any kind or means to request your certificate. And the responder can send, or the initiator can send a certificate request to the other side. And within the certificate request, you can state what kind of certificate authority you're willing to accept. So you can say, well, I want any kind of certificate you've got, or I want a certificate that has to be signed by this kind of certificate authority. What Checkpoint did was it sent a certificate, you could send Checkpoint a certificate request, and if you use the certificate authority within that request, which was a little bit too long, you had a buffer overflow in Checkpoint. So since all these payloads have got variable length payload, may be of variable length, you have to check all these lengths and check if the buffer is actually protected. So, what tools are available? I looked around and tried to find a tool which was already doing this kind of stuff. And what did I find? Well, I found IKE-Crack, which I already mentioned. IKE-Crack is a tool that is able to crack pre-shared keys used in aggressive mode. The same guy who wrote IKE-Crack, which can be downloaded here, also wrote a tool called IKE-Prober, which already did a little bit of that, what I wanted to implement. It is able to generate the first packet within the IKE exchange to test whether the responder is accepting pre-shared keys. So you've got a tool to test whether the VPN gateway you're trying to attack might be susceptible to the IKE-Crack snarf attack. Then there's a tool called IKE-Probe, which you can download here. And IKE-Probe is pretty much the same tool as IKE-Prober, just for Windows machines. So it pretty much tries to do a main mode or aggressive mode exchange using pre-shared keys. And the last one is IKE-Scan, which is somehow a discovery and fingerprinting tool. You can download it here. And IKE-Scan is a tool which tries to find out what kind of VPN gateway is used on the other side. So you can use IKE-Scan to test, is this a Checkpoint VPN gateway, is this Raccoon, is this FreeSwan? It's quite interesting how it does this, because it actually sends the first packet and doesn't respond anymore then. So it sends the first packet, responder answers, and doesn't get an answer back. And then the responder will repeat its answer. And IKE-Scan somehow times these answers and is able to use this timing information to find out what kind of VPN gateway we're talking to. What I did now is I wrote a tool which is far from complete. As you can tell, since as I showed you, IKE is very, very, very complicated. This IKE-Test tool is far from complete. What does it do? Well, it's written in Perl. I chose Perl at first because I thought it would be the easiest way to do it. Since I don't know who of you is coding in Perl, if you code in Perl, you usually assume that somebody already has written some kind of Perl module for anything you want to do. So I assumed that there would be several modules available to encrypt and to decrypt and to do Diffie-Hellman and all that stuff. And there are a lot of modules available, but not all you need. So I had to, well, somehow do some tricks to actually implement everything I wanted to do. I use especially a Perl module which is called netraw-IP. What does netraw-IP allow me to do? Well, I can create packets and just inject them into the wire and sniff the answers back from the wire. So I don't actually implement a UDP connection, but generate all my packets by myself and pass them afterwards all by myself. The fact that it was written in Perl, well, the idea was that it would be easy to extend and modify. In terms of cryptography, it's not that easy to extend and modify, and right now I'm trying to implement it all over again and to redo it. It strives to implement all different IKE messages, and it strives to implement all different IKE messages and all different steps within the protocol. So to just tell you what I want to do is, what you can do is there's this certificate request payload, and you can even send the certificate request payload within the first packet. You can send it in the second packet, you can send it in the third packet. And what I try to do is to implement all these different possibilities so you can choose where to implement or where to send the certificate request payload and the other payloads too. The tool will be available at this URL. It's not available yet there. I will put it there tonight or tomorrow. So you can download there the newest version of the tool. The tool on your disk you received is not the newest version. It still has a couple of problems. The newest one still probably has a couple of problems too. And it's far from complete, as I said. Just to show you a couple of examples what you can do with it. You can try to initiate now any kind of VPN connection. So here's the IKE-Test command, which targets this machine, uses a couple of transforms, and uses or encrypts the phase 1, which means that the last 2 messages shall be encrypted. So what you can even do, what I can do with the tool, I can say, well, I don't want these last 2 messages, well, my last messages to be encrypted. And using this non-encrypted last message, I can test whether the other side will accept it or not accept it. There are implementations that do accept it, older ones. I haven't found one at the moment. I'm still testing a lot of different implementations. You can define your certificate, you can define your private key you want to use, you can define the identification you want to use, you want to present the other to the other side, like ASN1, distinguished names, or IP addresses and stuff like that. Within the payloads, as I showed you before, there's a reserved byte. You can set the reserved byte to different values. You can check how the different implementations react on a set reserved byte. Usually this reserved byte has to be set to 0, and we can set it to any kind of value. And we can pass the output we get back, so you've got an idea what the VPN gateway sends you back. So let's just take a look at 1 or 2 of these implementations. Let's see if that works. So what I need now is I need a Linux box which is vulnerable. I start up a Linux. Would take a couple of seconds. So we've got a Linux. Let's see. This is a Linux box running on a. Oh, let's see. We can get this a little bit larger. I guess you can read it now. This is a Linux box which runs on a 2.6 kernel. The Linux 2.6 kernel is the first Linux kernel to implement IPsec within the kernel. And I've got a Raccoon version running on this box. Well, I can start it. The version I'm using here is based on the IPsec tools. If you implement or if you build Raccoon on Linux, you usually don't build the native Raccoon on Linux, the one from BSD, but there's a special port, a special Linux port of Raccoon, which is called the IPsec tools. The IPsec tools can be downloaded from SourceForge 2, and these are the IPsec tools 0.3 RC4, and I can start Raccoon. And I first start Raccoon using preset keys. I just want to show you that actually the tool works and can implement VPN connection. I've started Raccoon here with the debug switches, and I've told it to stay in the foreground so we can see what's going on. No. Okay, let's see. That's not what I wanted. Oh. Nah. Sorry for that. Okay. I'm looking for a preset key version. Good one. Okay. Okay, this one should work. To just explain the different options, this box, this virtual Linux box, which is running here, is its own Linux box. Maybe I should explain you what's happening on here. This is its own Linux box, separate from the box in the background. It's got its own IP address. This IP address is 5.0.0.1, and when I start Raccoon here and issue this command, I tell IKE-Test to target 5.0.1 using main mode, and using this transform. So the phase 1 will be encrypted using 3DES. Authentication will be provided using MD5. I will use preset keys for this authentication, and I will use Diffie-Hellman group 1. And I offer another transform. Since I initiate the connection, I can propose different transforms. And I propose another transform, and in the second transform, I exchanged MD5 by the CQ hash algorithm, and I can even propose the same transform twice to check whether the other side is able to cope with that. If it's able to cope with several identical transforms, I can even add 10, 15, 20 different transforms to check whether the other side can cope with this number of transforms. Then I define a preset key I want to use for the authentication. Debug gives a lot of information on the screen. Encrypt phase 1 tells the tool to encrypt the last message, and get rid is at the moment implemented in all versions of IKE-Test to get rid of a disclaimer shown in the beginning. So Raccoon is running, and now I start this tool. Let's see what's, oh, I'm in the wrong directory, okay. let's see what's happening. So a lot of numbers flowing by, and here's the information Raccoon is logging, and the last line tells us that a security association has been established. So this tool was able to establish a security association with Raccoon at the moment, and this is fine because if we take a look at the configuration of Raccoon, everything we did was okay, meaning we allowed anonymous initiators using main mode, 3DES, MD5, using pre-shared keys and diffie Hellman group 1, and the pre-shared key we used is okay too, since it is mentioned in this file. So everything is fine. Now let's check certificates. So I start the Raccoon again. Oh, this would be the configuration file for certificates. And let's start Raccoon. And let's check Raccoon using certificates. And what I'm doing here is I'm telling, sorry, that was too fast. What I'm doing here again is I tell the IKE-Test tool to target 5001 using main mode, using the transform. And for authentication, we now want to use RSA signatures. We want to encrypt phase 1. And this is a certificate we want to use. This is a private key we want to use. We want to use to sign the last packet. This is identification we want to use. Okay, we can get rid of this reserved here. We don't want to change the reserved byte. And we want to pass the output, want to see what's happening. And Raccoon in the background is running, and I start this, and everything should be fine. So again, we had, where is it? Oh, okay. Oh, great. This is German. The battery is fully loaded, fully charged. Okay. Where was I? Here. That's the log message I was looking for. And again, we have got a security association established using certificates. And again, this was fine since the certificate we used has been signed by the same certificate authority Raccoon trusts, and therefore we should be able to authenticate. Now, let's try something different. I start Raccoon again, and I tell my tool to use an arbitrary signature. Just use zeros as signature. What happens now is that the last packet that contains a signature will contain these zeros instead of the signature. So the last payload will have the static part, the next payload byte, the reserved byte, and the length, and then we'll just have these static zeros inside. And if I use that, Raccoon still says, wow, security association is established. Now let's see if we can see what has happened. Okay, wait. Oh. I have to, let's see if I can find it. That's all the debug messages of Raccoon. Okay, where is it? Ah, I'm not finding it at the moment. Ah, wait a second. No, I'm not able to find it at the moment. If you actually take a look at the Raccoon log messages, you can even see that the signature is set to 0 and still is accepted by Raccoon. Now, this was fixed in a later version of Raccoon, and I can show you that the later version of Raccoon is not susceptible to that anymore. So I start a different Linux box, which has a newer version of Raccoon. Excuse me? It's not implemented in the version which is on the web or will be on the web, but I'm working on it. I will tell you a little bit later what I actually want to still implement and what has to still be done and what has been done already. Yes, but vendor IDs are very important and are a must. Let's see. Let's get this a little bit larger. Now, this is a newer version of Raccoon. This is, although the number was 0.3 here, this is a newer version. There are two versions at the moment. The 0.2 version is a stable version, 0.3 version is a development version. This one is actually not susceptible to the attack, and we'll take a look at that. So I start my Raccoon. I hope this is the right configuration file. And what we do now is we try the same attack on a different target. This one has got the IP address 3.0, and let me show that to you. This is 3.0.01. So we target this box. Let's go. And wait a second. He's telling me he's got established this thing. Wait a second. I've got a small flaw here in my demonstration. This shouldn't happen. Let's try again. Oh, okay. It's not sign, it's sig. This is one of the flaws in this, this is one of the flaws still in the tool. If you define an option which is not actually recognized by the tool, it doesn't tell you. The option here to use is sign. And let's first try it again on the older one, that you still see that the older one accepts it. Okay. So the older one says, well, everything is fine. And let's see now if I can find now the signature. It's composed of zeros. Where is it? Maybe later. Okay, now let's try it on the second one. Okay, let's start Raccoon and try it on the second one. Go. And here we've got not an accepted security association, and here we find, let's see, here it is, invalid sig. So the newer version doesn't accept the signature and tells us, well, it's an invalid signature and rejects the connection. Now, let's attack the newer one again. And I'm not using a preset signature. My tool should calculate the correct signature, and I attack it again. And let's see. What I'm looking for now is a different kind of message. First, we see that the phase 1 has been established again. It's here, down here. And now, if we take a look further up, where the certificate is checked, Here the signature has been authenticated. And wait, where is it? It always happens if you stand in front. You never find what you're looking for. Oh yeah, there it is. First line. Certificate has expired by depth 0. So this certificate is, or was a valid certificate, but it's not valid anymore. The certificate has been expired. And Raccoon still accepts the certificate for the authentication. There's no way in Raccoon's configuration files at the moment to actually disable this behavior. There's no way to tell Raccoon, well, accept certificates although they are expired or although they have been revoked. So Raccoon just accepts them, revoked or expired certificates. There's now a newer version of Raccoon which will reject these certificates. But still, if you take a look at these errors in certificate handling, which have been in Raccoon for the last couple of years, you would expect that, well, the programmers should be able to find these flaws and errors and to fix them themselves. But essentially, or apparently, nobody actually tests its own his own code. These flaws were in Raccoon, in all versions of Raccoon, known to me before March this year. And if you think about who's using Raccoon today, well, most BSDs use it, apart from OpenBSD. Linux is using it, so if you've got Red Hat Enterprise Linux distribution, Red Hat Enterprise Linux is using Raccoon for its IKE messages. If you take a look at Apple, Apple is using Raccoon for its VPN connections. So even although Red Hat and Apple got into this stuff, which was only BSD before, these errors haven't been found. So that's why I think we need a tool to test this. Okay, well, let's see. Where was I? Those were the examples. And they showed you that the tool is able to test this stuff. Now, what can't it do yet? While developing this tool, I found out that implementing one tool to test both the aggressive and the main mode is much too complicated. So right now I've got two tools to test either main mode or aggressive mode. The aggressive mode tool is not fully finished yet. There are a couple of problems with that tool still. What both tools don't do yet is they are not able to generate any kind of vendor ID or parse vendor IDs. What are vendor IDs? Vendor IDs were implemented in IKE to allow vendors to exchange proprietary messages, so that if they wanted to test new bleeding edge features, they could implement them in their own software, and the software could negotiate this fact across the IKE channel. So the initiator sent a vendor ID, and the responder somehow recognized the vendor ID. It could use new additional features which are not present in the standard IKE protocol. Today, vendor IDs are very important if you want to implement something like net traversal, network address translation traversal. Sorry. What net traversal is, essentially, it allows you to send IKE and IPsec protocols across net devices. The problem with IPsec and net is that IPsec itself cannot be netted. Why not? It doesn't have any ports. If you take a look at modern net device implementations, they all use the port to keep track of the connections they have netted. Since it's not just net, but NAPT mostly today, network address and port translation. So those are not implemented yet. What else am I trying to do? Well, during the development of this tool, I found out that the approach I chose in the beginning is not very suited for this tool. And what I'm trying to do is to do a full overhaul and try an object-oriented approach, so it's much easier to implement the different messages and the different payloads and stuff like that. Again, what I need are more RFC compliance tests. You are already able to modify almost all payloads using the tool and to define them by hand manually with different length, but there's even more that you can do with it. And what I'm still missing is the base mode. What I'm still missing are some encryption algorithms which should be implemented in this tool. And what I'm missing is time to test commercial implementations. So that's what I want to do next. To just give you an idea what problems you've got if you implement such a thing with Perl. You need, and in some cases, you need encodings or signatures which aren't implemented in Perl yet, so you don't find any kind of Perl module to help you doing it. And since I don't want to code a 1,000-line Perl module to do just one task within my tool, right now I'm using sometimes external tools to implement parts of the IKE implementation. So here, for example, I'm using an external tool which is called FSW cert, which actually takes a certificate file and extracts the ID, the ASN1 distinguished name out of the certificate file, and the extracted ID has the right encoding for it, because you need, in the payloads, you need ASN1 DER binary encoded identifications. To implement that in Perl, well, I guess would be a couple of hundred lines to do it right, and therefore I'm using these external tools sometimes. Question? Yes, I'm using OpenSSL too. Wait. Here, for example, I'm using the OpenSSL RSA util command to sign the data to create a signature. What I first wanted to do is actually do a full Perl implementation to not be dependable on these external tools. And there are a couple of OpenSSL Perl modules, but most are incomplete. So therefore, I'm now using OpenSSL commands directly within the tool. And I think the object-oriented approach, if I actually redo everything and use the object-oriented approach, I'm able to encapsulate that a little bit more and to get rid of some dependabilities. We'll see. Other questions at the moment? Okay, well, anyway, that pretty much is it. So that's what's on my to-do list. And well, I would like to thank you for your patience and for listening in. I showed you 2 applications of the tool at the moment. There are a lot of more that you can do, can use. I'm still testing a lot of commercial implementations, and I'm looking for bugs there, and am further developing the tool as I go along, implementing what I need within the tool. If you would like to use the tool, would like to test the tool yourself, you can either go to the Black Hat website, probably. The tool will be up online there within a couple of days, weeks. I don't know how fast Jeff will be updating the web page. As I said, the tool on your CD, well, I wouldn't bother with it. And I hope that I will be able to publish the object-oriented tool within the next 1 or 2 weeks, depending on the time I've got to redo it. And if you want the up-to-date slides, I don't know if anybody followed the slides in the book. 1 or 2 slides have changed. If you want to have the up-to-date slides, you will find them on the Black Hat webpage or on this webpage. So, yeah, well, if you've got further questions you don't want to ask here, maybe want to ask private or whatever, you can always send questions to me. Best would be this email address, so I know you're referring to the tool. Okay. Any further questions?
Did you test it against Pluto? And if so, did you find anything interesting?
I tested it against Pluto, and I think within the open source implementations, Pluto is probably at the moment the best, especially concerning X509 certificates. That's what I'm mostly interested in because they are the most errors can occur, probably. And Pluto and the X509 patch by Andreas Steffen is probably, at the moment, the best known X509 implementation to me, but I'm just testing the other commercial implementations at the moment. What I've tested so far, for example, is Microsoft, and from the outside it looks quite all right. There are no funny things and the packets get back. I'm starting testing Checkpoint, and I'm not quite sure there. We'll see, and a couple of other implementations too. But Pluto is, well, at the moment, mostly I use Pluto as a reference. So when I develop my tool and want to test new features, I must have a reference on the other side to see what I'm supposed to get back, and if everything I prepare has been prepared correctly. So mostly I use Pluto as a reference at the moment, and haven't found any funny thing in Pluto yet. So I guess Pluto is quite all right, although there was a slight flaw within in Pluto. There was...
There's 3 flaws in the last couple of weeks.
Yeah. There were some flaws within the last couple of weeks, yes. But those were mostly found by looking at the source code. Excuse me?
Do you support certificate change or just single service?
Well, I don't check the certificate I get back with at the moment within my tool, because I want to check the other side if that would support certificate chains. Yes, you can use any kind of certificate. You can, what you can do is, where is it? You can use any kind of certificate here and test whether the other side supports certificate chains. And if the other side then requests another certificate, I could send that too. Yes. To implement what? Not yet, no. It would be very interesting, but no, not yet. It's on the further down list.
Just above IKE-2?
Excuse me, IKE-2?
Just before IKE-2 on your list?
Probably, yeah. Further questions? Okay, well, thank you.